Let's get started with the problem that I guess many of you know, which is the knapsack problem. In the knapsack problem, we're given a set of one-dimensional items, and here the height of these bars indicate the size of the respective item, and we're given a one-dimensional container. Again, the height of this bar indicates the size of the container, and every item has a profit. And our goal is to select a subset of these given items that together fit in our container, like here the orange item, the green item, and the blue item. And our goal is to maximize the total profit that we get from these items. Now what I want to do is I want to look at a generalization of knapsack. And in my generalization, well, one way of looking at it is that there is a time axis, and such every item needs the knapsack only during a certain time interval. For example, it could be that the blue item needs the knapsack between this point in time here and this point in time here, and the green item needs the knapsack between this point in time and this point in time, and similarly the yellow item. And like before, every item has a certain profit that I get if I select it. And now I also allow that the capacity of the knapsack can change over time, and the capacity of the knapsack over time is indicated by this profile that you see here. And there can be also other items in my instance that have not selected, and again, these items can have profits. And now my goal is to select a subset of these items of maximum total profit, such that they fit together into the knapsack, into this time extended knapsack, meaning that at every single point in time, the total size of the items that are active at this point in time. So for example, for this point in time, this would be the blue, the green, and the yellow item. Their total size is at most the amount of capacity that I have available at this point in time. Okay, so now this problem is called unsplittable flow on a path in the literature. And now you might ask yourself, why is this problem called unsplittable flow on a path? Where are the flows here? Well, what happens is that typically this problem is defined on a path where every item that I'm going to call tasks from now on is specified by a start vertex and an end vertex, and these capacities here that you see here correspond to the capacities of the edges. So for example, this first edge here would have this amount of capacity, or this edge here would have this amount of capacity. Yeah, so for the green task, this would be the start vertex, this would be the end vertex. Similarly for the blue task, this would be the start vertex, this would be the end vertex, and similarly for the yellow task. And now one way of interpreting this is that every task is actually a commodity in a multi-commodity flow setting, and a commodity wants to send a certain amount of flow indicated by the height of these rectangles here. And if we select a commodity, the commodity must send all its flow, and we get a profit from this commodity. And we must make sure that our edge capacities support the total flow that we send from our selected commodities. Another application of this problem actually comes from scheduling, because you can think of this capacity profile as a profile of a given resource that is available to you, whose availability can change over time. So for example, energy or bandwidth that you might have, or amount of workers that you have that work for you. And now you can think every task as being a job that you might want to schedule on a machine. And let's say you have a large number of machines that don't form a bottleneck, but what you must make sure is that every single point in time, you use only as much of your available resource as you have available. Yeah? So every job needs a certain portion of this available resource. What do we know about this problem? Well, the first non-trivial approximation guarantee for this general case of the problem that I just defined was an order log n approximation algorithm. Then this was improved to 7 plus epsilon, then further to 2 plus epsilon, then further to 5/3 plus epsilon, and then to finally essentially 1.269 plus epsilon. However, there are reasons to believe that we can do better, that we can find a PTAS for this problem, because there are QPTASs known for the problem, so 1 plus epsilon approximation algorithms in quasi-polynomial time. However, it had been an open question whether we also get a 1 plus epsilon approximation in polynomial time, and this is the result of our paper, because we present a PTAS for unsplittable flow on a path, and here everything that I'm showing you is joint work with my co-authors Fabrizio Grandoni and Tobias Mömke. Now, for the sake of this presentation, I want to make some assumptions. First of all, I want to assume that the capacities are all uniform over time, or say every single edge of the input has the same amount of capacity. And I want to allow myself to use a bit more capacity than there actually is. So I want to allow myself to violate the capacities by a factor 1 plus epsilon. So this is a setting of resource augmentation that I'm interested in here now. However, I'd like to mention that even for the simplified setting, the best known results that are known are still the ones that I've showed you in one of the previous slides. So now what I want to do is, like, on a very, very high level, I want to use an approach that works as follows. I want to order my input tasks increasingly by their start points. Yeah, so as you can see here, and I want to consider them in this order one by one. And in this order, I want to decide one by one whether I want to select a task or not. So for example, here I would start with the blue task. I would decide to select the blue task. I could still decide to reject the green task, or not to select it. I could decide to select the orange task, to select the red task, reject the purple task, and so on. Okay, so this is not yet an algorithm. This is just some high-level approach because I haven't specified how I want to decide whether I want to select a task or not. So one thing you can do in order to decide this is to use a dynamic program, because suppose we are at this situation here where the next task to decide is this green task here. Then what happens is you can draw a vertical line here that goes through the start point of the green task. And you can then, the remaining sub-problem you have to solve is that you have this amount of capacity available, where some capacity is taken away by previous selected tasks that stick in here from the left. And our goal is to decide upon the tasks that are completely on the right of this vertical line and decide whether we want to select them or not. And now what happens is, for this question, the tasks that are completely on the left of this vertical line are actually completely irrelevant. Like, for example, this blue task is completely irrelevant, so we can as well forget about it. And similarly, this green task here. And now what happens is, what you would do, you could set up a dynamic program that has a dynamic programming cell for each subproblem of this kind that is specified by a vertical line, by a set of selected tasks or previously selected tasks that cross this vertical line, and all the tasks on the right. And then you could, if you want to decide whether you should select the green task or not, you could say, okay, there are two options, either I select it or not, and in either case, this brings you to some other DP cell. Yeah, so for example, if you select this green task here, then the remaining subproblem is specified by the cell that you obtain by moving this vertical line to the right to the next start point of the task, and then you can have a smaller area of remaining space, and you can delete some of the, can forget about some of the previously selected tasks. Okay, so now this is an algorithm that works perfectly well. The problem is, of course, it is very slow because the number of DP cells can be exponential, simply because if you fix one vertical line, the number of possibilities for tasks that you selected previously that cross this vertical line can be up to 2 to the n. Yeah, so this is very slow. So therefore, we need some new ingredient, and our new ingredient is actually a game, or to be more precise, a game that I would call the game of unsplittable flow on the path. How does this game work? Well, this game has a player, but in contrast to other games that you might have played before, there are no other players or adversaries or anything. It's a solitary game. And in this game, the player is given an instance of our problem. Yeah, so the player knows the entire instance up front. And these tasks are presented to the player one by one. And in this order, the player has to decide to select a task or not. So for example, this player, and yeah. Also, I want to distinguish between two types of tasks. One type is what I call large tasks. These are tasks that use a constant fraction of the available capacity, and a small tasks of all the other tasks. So what happens is there's a fixed threshold that tells us whether a task is large or small. Now, when the player plays the game, he starts with a blue task and has to decide whether to select it or not. So suppose he selects it, And then maybe he decides to reject the green task. And then suppose that the player decides to select this small orange task here. And now when the player selects a small task, something maybe unexpected happens, which is we throw a coin. And depending on the outcome of this coin flip, we round the task up or down. So either we round it up so that it occupies its size becomes a constant fraction of the available capacity, similar to large tasks, or we round it down to 0. Okay, so suppose and this coin flips, this coin is biased such that in expectation, the rounded size of these tasks is the same as the real size of the task. Yeah, so in some sense, we introduce some variance here artificially. So now suppose this task is rounded up, then we proceed. So maybe the player selects the red task and then rejects the purple task and rejects the yellow task, and the game goes on. Okay. Now this is what I would call the UFP game. And now what I want to do with this game is the following. First, I want to argue that I can compute the optimal strategy for playing this game efficiently in polynomial time. Secondly, I want to argue that there exists a strategy to play this game whose expected profit is essentially as good as the offline profit of the given instance of unsplittable flow. Okay. Note that the profit that the player makes is random because this depends on the coin flips. Yeah. So intuitively, if many tasks are rounded up, then they occupy a lot of space, and then you cannot put more tasks into the space. However, if many tasks are rounded down, then the player kind of gets lucky and probably gets more profit. Finally, I want to argue that if you give me a strategy whose expected profit is at least some value alpha, some number alpha, then I can transform this strategy into a solution of my given instance whose profit is essentially the same. Okay. Suppose for a second all this was true. Then what I could do is I can compute the optimal strategy efficiently. I would know upfront that the expected profit of the strategy is essentially opt, because there exists a strategy that is that good, and my strategy is the best strategy. And then I could take this computed strategy and apply this argumentation, this routine on the bottom, and transform it into a actual solution for my given instance whose profit is then again essentially the same as opt. Okay, so let's look at these steps one by one. Let's start with the first one. The first one is actually relatively easy because I can use the same dynamic program from before, but now it works. Why? Because I can still say, okay, if I have a situation like this one here, my next task is the screen task, then my remaining problem is to use this space here as good as possible by selecting more tasks. I can, like before, I can forget about tasks that are completely on the left. Like before, I can for tasks that actually cross this line. All I need to remember is those tasks that I've selected that are rounded up, that cross my vertical line here, and then the number of DP cells is actually bounded by a polynomial. Simply because I can have only a constant number of large or rounded up tasks that cross this vertical line here. So there are only n to some constant many possibilities for this. Okay, so that was relatively easy. Now I want to argue that there exists a strategy whose expected profit is large. It's essentially opt. Why is this? Well, my strategy does what you might expect is what you do is you select all tasks from opt. Note that this is an existential result, so I can say things like I assume I know opt, and then based on this, I design a strategy. I only have to show that such a strategy actually exists. Okay, to be a bit more precise, I select all tasks from opt that actually I can take. What I may mean by this? Well, what could happen to me is the following. It could be that I select a small task, it is rounded up. I select another large task, I select another small task, it is rounded up. I select another small task, it is rounded up, and so on. And then if the next small task comes, then what happens is I cannot select it because there is a risk that this task is rounded up and then it would not fit with the others. So then it's the detail of the game, that's an important detail. The game says then you're not allowed to select this purple task, so you cannot pick it. However, you can show that this is actually very unlikely to happen. And the reason that my picture is a bit misleading, because what happens is that if my additional capacity is, say, delta, then the sizes of these rounded up tasks are much smaller than delta. So in particular, if I round my task from opt, then I can say that my tasks from opt with their actual size that fit into the given capacity. And if they do not fit even with this additional capacity, then I can say that I can argue that this happens with only some probability epsilon, some concentration arguments. So therefore I can say the probability that any task I in opt is not selected is at most epsilon. So therefore my expected profit is essentially opt. Good. Now let's talk about the last step. And yeah, unfortunately, I don't know whether this is true. I don't know how to show this. I personally would believe that it is true, but we don't have proof. And let me give you some intuition why this is not obvious. Well, the maybe first thing that one would like to use is the following. Suppose the player plays the game. Okay. So then there are some tasks that the player selected, like these tasks here. Then there might be some other tasks that the player did not select. And there could be some other small tasks that the player selected that have 0 size because they were rounded down. Okay. Then it is true that for every single edge, every single point, the expectation, the size of these rounded up tasks is the same as their real size. So I could say something like I just pick every task that the player selected. However, you could even say that it's with probability at least 1 minus epsilon, the rounded size is essentially the same as the real size, but it's not good enough that this is true for one single point. You want it to be true for every single point, and this is not clear how to prove that. Okay, so therefore I don't know whether this is true. However, in the previous paper we showed that something similar is true with some slight modifications of the game. So there we show that you can actually turn a strategy with expected profit alpha into an actual solution by losing this factor e+1 over e+2. So this then gives a 1.26 rounded approximation algorithm. Okay, but I promised you a PTAS, so I should give you a PTAS. How do we do this? Well, what we need is a game of U of P, but let's say the version 2.0, a more sophisticated version. How does this look like? Well, my more sophisticated version of the game has a more sophisticated player. This is my more sophisticated player. And the game works as follows. I again start out like the previous game. So I show the tasks one by one to the player. So maybe the player now rejects the blue task and rejects the green task, and then picks the orange task. And now again, I flip the coin. And now if the task is rounded up, something different happens. Maybe what happens is now I split the game into 2 sub-games that I play independently. And how do these sub-games look like? Well, I ask the player to specify some decreasing profile with only a few steps, which then yields some blue area here. And the remaining area that I can use is this red area here. And both of these areas correspond to sub-games, and they're defined as follows. I draw a vertical, like a purple line at the end point of this orange task. And I say for this blue sub-game, also I say for this red sub-game, I have as input all tasks that are completely on the left. And for this right sub-game, I have all the tasks that either cross this purple line or that lie completely on the right, like this red task here. Now, for the tasks that cross this line, I change their order such that they're ordered decreasingly by their right endpoint. And another thing changes, which is if I select a small task and it's rounded, and I still flip a coin, but its size is rounded only randomly on the right. So only on the right it's rounded up or rounded down. On the left it still has deterministically its actual size. Okay, so now this game is of course more complicated, but you can still show with very similar arguments that you can compute the optimal strategy efficiently. You can still show with very similar arguments that, as before, that there exists a strategy whose expected profit is essentially off. And now with actually a lot of hard work, you can show for this game that if you give me a strategy with expected profit alpha, I can turn it into a strategy with profit at least essentially the same as alpha. So now, as before, we can argue we can compute the optimal strategy efficiently. It will have a profit and expectation of essentially opt. And now with the last routine, we can turn the strategy back into an actual solution for our instance, whose profit again is essentially the same as opt up to a factor 1 plus order epsilon. So now everything I showed you was for the simplified setting out uniform capacities and resource augmentation, but of course you want to have the setting without resource augmentation and varying capacities. And here we use a tool that we also used in previous work, which is what we call the slack lemma. This is some tool that intuitively allows you to trade a factor 1 plus epsilon for a weak form of resource augmentation, and turns out that this weak form of resource augmentation is good enough for what we want to do. And then the game becomes much more technical because of this transformation. But overall, what you obtain is the 1 plus epsilon approximation algorithm for unsplittable flow on a path in polynomial time. Thank you very much for your attention.